Hello and welcome to another demo for the mechanism design exercise. In this demo we'll be creating a multi-bar mechanism and then determining the torque we will need to hold it stationary. In your exercise you'll need to understand what this torque is and what torque you'll need to overcome to actually make your car convertible roof mechanism deploy. So without further ado we will start up MATLAB and create a new model. So in the MATLAB command window, just write sm new to create your new model. Okay, so this is our new empty model space, and on the right here we have all the mechanism blocks from your template models, and we will be using some in this exercise. First of all, let's clear the workspace and just keep the global parameters, and we will go and edit these now. So the first thing we want to do is to change the gravity so it's acting in the y-axis, because actually our device will be swinging a lot on the y-axis. So we just change that gravity, click apply and click OK. The other aspect we want to change is in the simulation model configuration parameters. We go into these parameters, let that load up. We want to select the solver that we're going to use for our case. Just have to let that load. Sometimes it takes a while once you've just first booted MATLAB. There we go. So we want to do a, so first of all we want to do a fixed time step, and we want to use OD for running cutter. We'll keep the start time from 0 to 10, and if we go to the additional parameters, we'll set a fixed time step of 0.101 seconds. And we click apply, click OK, and that is all our configuration set up for the model. Now we actually want to add some blocks and create the mechanism that we are going to simulate. So the first thing, if you double click, you can put up this search tool to actually get your blocks from Simulink, and what we want to do is request a revolute joint, and we're going to stick that to our 0, 0 weld plane. There we go, just paste that there. Okay, so now we've got a revolute joint on our 0, 0, 0 point welding space. We also want a rigid transform. We're going to also click that on the onto our 0, 0, 0 in our weld space. If we double click this, we'll set a translation, and we'll use the Cartesian coordinates, and we'll set an offset of minus 0.1 meters. Okay, and you'll see this in a moment when we do our multi-bar mechanism. It's going to be connected at 2 points along this axis. So that's our revolute joint and our rigid transform. So now if I go and collect a beam from our mechanism blocks and copy and paste that in. There we go. And let's double click it and we can set some parameters. So I want this to be length of 10 centimeters. We're just going to give it some nominal width and height of 1 centimeter so we can actually see it in the viewer. And we're going to give it a density of 1,000 kilograms per meters cubed. Again, these are just arbitrary values just for the demo. In your mechanisms, you'll need to make these more realistic to the actual mechanism you're designing. So we'll just click apply and OK to that, and we'll join that to the revolute joint. And what else we can do is just double click this revolute joint, and we want to specify a position target for where it starts for our simulation. So we're going to set this to 45 degrees. And it's going to be the high desired because that's the one that we want fixed, and all the other angles will resolve and sort themselves out so that we get 45 at this revolute joint. So we'll click apply, click OK, and just to see what we've done so far, if we go to diagram, simulation update diagram, and I move this to the right. There we go, it's just saving that for us. Compiling the blocks, and we should get the view coming up into MATLAB in a couple of seconds. Here we go. Should be here in a second. There we go. That's it. So again, when you first boot up MATLAB, it takes a while just to first boot, but once you've got it up and running, it should be a lot quicker to create and update these models. So if we I just clicked there the side view. So actually we can see that the y-axis is acting in vertical, hence why we've got gravity acting downwards. And we've got our x-axis and the z-axis coming out of the screen. And actually, as you can see, we've got a bar at 45 degrees in our model space, and we can spin and look it around if we wish. So that's all well and good, that's great. So we've got our first bar in there. Now what we want to do is create another couple of bars and complete this mechanism. So actually I'm just going to copy and paste this bar. We'll double click and add another revolute joint. We're going to connect these two up. There we go. Copy and paste again, and we are going to get a couple more revolute joints. We're going to have one fixed to the rigid transform, going to our beam, and one more to connect the two beams together. And there we go, that is just our simple mechanism. Once we copy and paste, it keeps all the variables the same. So as you can see, so actually I'm going to change the colour just so we can see what the different beams. So that one will be green, and we will change this one to red. Click apply and OK. And if we go to update diagram now, as we can see, there we go. So we've just created. Let's just use our views to. That's it. There we go, to auto scale it into view. There we go. So that's our simple mechanism fixed at 0, 0, 0, and minus 10 centimeters here. It's fixed with a revolute joint, so it can actually spin around that axis. And then we've got joints connecting the green and red and the green and blue. So that is all ready to go. We should be able to simulate this now, and what we'll see is it just swinging due to gravity. And there we have it. So that's our simple mechanism. That's all jointed up, and it's just swinging against gravity. So now we want to understand how we can work out what torque we require just to keep it in that position. So if you're looking at your car convertible roof, that'll be the torque it would need to overcome to start actually deploying, or for to retract. Okay, so with your car convertible roofs, you're going to have lots of multiple bars, and yes, you could calculate that manually using your solid mechanics notes, but it would take you a long time. And actually, this is what the power of using these models is. It's actually to generate these torques for you. To do this in this model, we're going to use the advantage of this revolute joint to actually determine the torque we required for a specific position. So what we're going to do is go into the revolute joint. We are going into sensing because we want to get the torque coming out of this. And we're going to have actuation, and we're going to have, rather than selecting the torque, we're going to select the motion, and we're going to say provided by input. And what we actually do is that we're not going to set any motion. Actually, we're going to say a specific angle that we're going to maintain it at. And then it will actually compute the torque which is required to maintain that angle for our mechanism. So we click apply, click OK. We should get a couple more arrows coming from our revolute joint. Now if I bring this over, and we'll just start using some of our blocks from our mechanism. We'll want a S to PS converter. And I will flip this block to make it easier for us. There we go. So that's going to go into our demand for our angle. We're actually then going to use a constant. So we're going to actually set this angle for our model. There we go. And this was going to be pi by 4, or as you know, this will be 45 degrees. So the same angle that we specified in our revolute joint. So we want the model to set up at the right angle, and then we want it to maintain that angle. Okay, so this, just go here. And now the last thing we want to do is a S to PS. Oops, the wrong one there. Yep, PS to S converter. Sorry about that. There we go. We're going to get the torque out, and then we can actually deliver that to a scope. So copy and paste that to a scope, and we should be able to determine the torque we require to actually keep this mechanism stationary. So we just have to now click run, and if we've got everything all connected up, we have just a slight error there. Bear with me there. Just double check the settings. Aha, sorry about that. Yep, there we go. I just had to double check on my other model. The actuation, of course, torque is none, is actually going to be automatically computed. So we wanted to switch that round. We're going to get the computer to compute that for us. Otherwise, we're saying there's no torque, but we want to fix it to position. And it's just thrown an error saying, actually, we have an issue. We can't actually resolve that condition. So if we click OK now, and there we go. That's fantastic. So now we've got the model. Like I say, it's not actually doing anything because we're just holding it in position. And we can see it's simulating for the full 10 seconds. If we go and check the scope, so we double click that scope, we should be able to get out the actual torque that is required to maintain that position. And there we go. So it's just below 0.014 Newton meters. And that's it. There we go. So that is a quick demo just to show how you do a multi-bar mechanism. And then from setting it into the position that you want it to start in, and then fixing it into that position, and then determining the torque that you would need to overcome to actually move it out of that position. So for your case, once you've determined that, you can actually then look at the motors and look at the gearbox ratio that you would require for your mechanism to start moving. Okay, thank you for watching, and I hope that was really useful. Okay, goodbye.